Let's talk about logarithms. Originally, the word was logarithmus. I believe it was coined by a famous Scottish mathematician, John Napier, back in right around 1600. Long time ago, way back there with Newton and those other giant mathematicians. But a logarithm is a huge tool, especially in science, and it works like this. This is a, right here, this b to the x equals n is an exponential equation, right? Base b, x is the exponent, and n is what I call the target number. It is exactly the same as log base b of the target number equals x. I'll say that again. B to the x equals n is exactly the same as logarithm base b of n equals x. So memorize this transformation formula from exponential equations into logarithmic equations, and that'll give you the power to solve about half of the problems that we're going to be going through here. Let's do an example. Right? 3 squared, 3 raised to the second power equals 9. That's the exponential equation, and a logarithmic equation would be log base 3 of 9 equals 2. Okay? 2 is the logarithm. In other words, 2 is the exponent. So remember, logarithms are exponents. And the base number is whatever the exponent is being applied to. That's the base down here. And this is what I call the target number. Different books give them different names, but it really doesn't matter what you call them as long as you know how to use them. Let's practice with a couple of more, changing from exponential equations into logarithmic equations and vice versa.
How to change your exponential equations into logarithmic equations or logarithmic functions, and backwards and forwards. So here's the big example is, if you have an exponential equation in this format, the b, base, some number raised to an exponent equals some big number or small number, then we rewrite that in logarithmic form as this, right? Log base b of some big number n is the exponent. So a logarithm is in fact an exponent. So let's go ahead and do a couple problems. So our base is 3, that's going to be the base over here. Our exponent is 4, that's going to be your actual logarithm, and then 81 is going to be your big number. So you just kind of replace, plug and chug. So they're the same equation, except for one's in exponential form, the other one's in logarithm form. Let's do another one. Kind of ugly again, but same thing, right? The 1/4 is the base, the 64 is the big N, and -3 is the actual logarithm, is the x. So we just substitute, and we get the exact same thing. Yay. And let's work backwards. If we get one that's a logarithm form, we just replace the 6 for the b, because that's the base. Your n is 216, and your 3 is the x. So that's how you shift them around.
You might be asking yourself, why did somebody invent logarithms? Besides to torture math students, that is. Yuck, yuck, yuck. But they are very, very helpful when talking about huge numbers or really, really, really tiny numbers. So let's take a few examples here. Earthquakes. And we're down here in San Diego. We get them all the time. Earthquakes are measured with Richter scales. Richter scales are logarithms. Okay? So here's the Richter scale graph. And let's say we had an earthquake of 6, right? 6.0 on the Richter scale. It's actually 10 to the 6. That would be this one right here, which is between a moderate and a strong earthquake. And as coincidence would have it, today, the day I'm making this video, is the anniversary of the very highest earthquake ever recorded, a 9.1 back in 2004. That's when that big chunk of underwater mountain fell and caused that Indonesian tsunami of 100 feet and killed all those people. It was horrible. But that was a 9.1, and that's literally 10 to the 9.1. So let me show you what that would look like on a calculator, right? We'll take 10 and we'll raise it to the 9.1. Bam. Holy guacamole. And that would be I believe 10 to the 1 that's 10, obviously. But I think that would be a 1 earthquake is 10 pounds of dynamite, which isn't very much unless you're standing real close to it. Then, of course, it would be very much. But an earthquake of 1 is unfeelable. We have them all the time down here. But what this would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be 1,258,925,411 pounds of dynamite. That you would feel. And unfortunately, all those poor people did. But let's keep moving on here. Okay. And another use of logarithms are for pH balances when it comes to acids and bases. If you remember your chemistry, if you haven't had it yet, that's what you're going to be doing here. And here is a table for hydrogen activity and oxygen hydrogen activity. So if they have a pH balance, a low one, less than 7, it's considered an acid. And if it has a pH balance of greater than 7, it's considered a base. So what it is you look at this base, right? This is 10 to the negative 14. So in other words, there should be 13 zeros in front of that 1, which means it's a little bitty tiny number. So we don't want to write these little tiny numbers. We just want to simply write the logarithms of these guys. Now, a logarithm can have any base it wants, but the main two that we're going to be using, and most science uses, there's only 2 types of logs. The first one is what we call a common log, which means that the log is base 10. And it kind of looks like this. Log base 10 of 1,000 is 3. But mathematicians, we get kind of lazy, right? If it's not written, if it looks like this, log with no base, then it's assumed that the base is 10. Okay, I'll say that again. When it's written log of some number, when there is no base written, it is assumed to be base 10. It is assumed to be a common log. Okay, again, mathematicians, we get kind of lazy. Like we don't write exponents of 1 anywhere. So if you don't see an exponent, we assume it's 1. If you don't see a coefficient of a factor, we assume it's 1. And again, if you don't see a base of a logarithm, we assume it's 10. Okay, natural log. These are the ones that make everybody cry. But there's a number out there that I'm going to explain here in a later video. It's called E. E is roughly 2.72. Consider it like pi, right? The relationship between a circle's circumference and its diameter, right? Pi is a non-ending irrational number, 3.14, blah, 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 blah. So E is similar to that. It keeps popping up in all these different calculations and discoveries. So there's something about the number E that explains something about our universe, but I don't think we figured it out yet. We have with pi, but we haven't with E. So here's an example. Log base E of this number, 54.74, is roughly 4. I had to put that roughly in there because I had to do some rounding. But now, we don't write the log base E like that. We write it like this. Boom. And it's just called the natural log. So this is the natural log of 54.74, roughly equals 4. And these are the important things that you should know about logarithms. That the log of 10 is 1. The common log of 10 is 1, right? Because that's the base of 10. And if we put this back in exponential form, that should clear it up for you, right? 10 is the base. The exponent is 1. And that equals the target number, right? So 10 to the 1 equals 10. So remember, log of 10 equals 1. And let's switch over to the logarithm, the natural logs. Same thing. You got to know this, that the natural log of E is 1. And remember, natural log, you can just rewrite it log base E of 1. And if we put this back into the exponential form, there's the base, E. We raise it to the exponent, 1, and that equals the target number, E. So just remember those basic things. And that's it for the basics of logarithms. And we're going to go into a lot of detail during this section. MGZ, out.